Hello, welcome. My name is Dr. Ayanna Howard, and I am a Motorola Foundation professor at Georgia Institute of Technology. And today I'd like to introduce you to the world of healthcare robotics with an emphasis on therapy. So the fact is that if you look at what's considered a disability in life, most individuals think about classical disability. So it might be a veteran who has an amputation, or it could be a child who is born with a developmental disorder. But the fact is that when we talk about healthcare robotics, when we say disabilities, we mean a change in your normative function. So if you were young and you were the best tennis player in the world, and then you turn 50 or 60 and you get arthritis, and you still want to play tennis, and you can't, then that is considered a change in your functions, a change in your quality of life. And so that would be something we would classify as a disability. It's not a classical disability, but it's something that you want to enhance your quality of life. And so when we say healthcare robotics, we look at how do we provide robotic services for individuals such that it improves their quality of life, whether it's acquired disability or a genetic disability. And so in the realm of healthcare robotics, where we're trying to push is these robots that can be used in the home environment, such that you can go to your local, Walmart or Target, and you can go and next to the room of vacuum cleaner, you have your healthcare assistant, and you purchase it and you bring it home. And so the concept is how do you provide robotics and build robotics and deploy robots that can be used in any environment, the home as well as the clinic and the hospital. And how can you have these robots used with a variety of individuals, whether they're elderly, whether they're children, whether they're just typical adults in 20 to 50 year range. But they have to be robust in this field. And so if you think about healthcare robotics, it really is the robots for home, work, and play. Every scenario where a human would go, whether it's at work, whether it's at school, whether it's at home, how can you have that robot assistance that provides it? And so today I'm going to focus primarily on one aspect of healthcare robotics, and that's in therapy. And so therapy is this process, and typically is done by humans, where you have an impairment, maybe you got hurt, maybe it's a sports injury and you just have to go through some therapy, maybe you are recovering from stroke and so you have to go through therapy to improve your motor skills, your reach, your grasping. And the typical scenario is you go to a human therapist, clinician, and they work with you. And typically when you first have the disorder or the impairment, you see the human therapist at a regular basis, and then as you improve, those services go away. But they've shown that the more therapy you have and more consistent that you have, you actually improve your motor function. And so if we could afford to have a human therapist with us 24 hours a day, every day of the week, we can actually improve much better than we can now. But that's not a reality. There is not a human therapist that's going to live and remind you every 10 minutes to do your therapy and every day. And so robotics can really fill that need, which is why there's a growing interest. So the clinical world, the therapy world has seen technology, has seen robotic technology and robot therapists as a way of filling the gap so that they can also provide their services to their patients, but then they can offset it for the home and have these robot therapists. And so I'm going to talk a little bit about what does that mean for robotics. How do we allow that and enable that to happen? Because now you have this component of you have a therapist who is the expert, you have the individual or the patient that the robot has to interact with, and the robot has to be part of this clique, this triage of human therapist, human patient, and this robot. And so there are some challenges. Primarily, if you think about the challenges, is in the clinical world, you have to prove certain things. And so if you have a technology, so I can say it's the best robot technology in the world, it looks cool, it does all these nice things, but if I cannot say, well, guess what? It improves your patient's movement coordination by 20%, then the clinician, the therapist has no interest in it. So how do you provide a robotic service and also prove that, it really does work? So that's one of the challenges. The other challenge is you have this clinician who's typically not going to be a roboticist, not going to be an engineer or computer scientist. How do you have the therapist communicate to the robot the protocol, i.e. what is it that I want you to do with this patient when they're in the home environment? And you can't expect a therapist to come to the terminal and start typing and programming. So what does that look like? Is it natural language? Is it some type of web-based interface? So that's one of the challenges. The other one is when the robot is in the home environment, what does the robot do? How do they interact with the patient in order to do what the therapist would normally do in the clinic or the hospital? And then third is that the robot has to report back. And so after the robot interacts with the patient, how does the robot provide that information back to the clinician or therapist? Because they have to know. They have to know that, Mr. Joe did this or did not do this and how well they did it and how effective it was, so that the therapist can then either change the protocol for the robot, or when Mr. Joe comes back to the clinic, the therapist can say, well, I know you did this right. We're going to move on because you've acquired what I needed you to do. And so there has to be this communication back. I'm going to talk specifically in this case about children, primarily because even though children and older adults have some of the same characteristics in terms of what kind of therapy, which is repetition, 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 children have a unique characteristic because they're still developing. So their brains are still mapping, they're still learning. And so you can think of it as when you have a child, you really are ideally mapping new information and new knowledge. And so for a robot, this is very interesting. This is very engaging. But you have to make it repetitive, but you also have to be engaging. Children with CP is one of the largest demographics of disorders that affect motor skills. That's from developmental, so you're born with it. And most children, whatever their disability, they go through therapy. So as soon as they're diagnosed with whatever, whether it's traumatic brain injury, so it's acquired, or they're born with it, they go through therapy. And they go through physical therapy, they go through occupational therapy, they might go through speech therapy, but they go through therapy. So this is part of their regimen. This is what they do. They go to school, they go to home, they go to their therapist. And one of the things about children is they're naturally growing, they're naturally curious. And so the therapy, unlike an adult, you can tell an adult, I need you to do this 10 times over and over and over again. Most adults will say, okay, a child will not do that. A child will do it once, maybe, and then a parent might have to come and maybe they'll do it again. And the therapist might say, I need you to do it one more time. But a child is not going to naturally do something that's boring. And so therapy for a child has to be engaging and interesting to the child. And so the motivation for robots in this regard is robots are really good at repetition. And so therapy is about repetition, doing something over and over and over and over again. Robots are good at that. Robots don't tire. They can do something over and over and over again and change it just a little bit, but still have the same therapy objective. The other thing is robots, they're compliant. Robots will not argue with you. And so if a therapist says, I need you to do this activity with this child, and this is how I want you to do it, you can program the robot, and we'll talk a little bit about what that looks like in order to do this. And so a robot really functions as an ideal scenario. The other thing is robots are engaging. For children, robots at this point in life are naturally interesting. They're like toys, they're like playmates. And so you can actually capitalize on that natural interaction to then encode the therapy. One of the biggest challenges as well is that children in general do not pay attention. And so, and this is an acquired behavior. Us learning how to sit in a room and listen to a lecture or a speaker is actually an acquired behavior. We are not born being able to pay attention. And its reason is because we're learning. And so for us, changing attention is really necessary for us to learn and to look and pay attention to this and pay attention to this. Because what's going on is we're starting to correlate things. Oh, I see a bright light. Let me look at that. Oh, I see another bright light. Oh, because the door is open. And so that's the way our brain works, that whole excitement and shifting in order to learn. And so we can't force a child to basically do the same thing over and over and over again. This actually goes against what is their natural evolution. And so for a robot, we have to figure out, how do you make something that could be boring, i.e. therapy, how do you make it so it's exciting and different every time, but yet it's the same in terms of the therapist or the clinician's mind. And so this is a challenge as well. And so the overall gamut of what we're looking at when we're talking about healthcare robotics and therapy is, one, we have to have something that's interactive and child-friendly, i.e. the robot. We have to be able to give something that's quantifiable in terms of metrics, i.e. what did the child do in terms of kinematic structure, how many times did they do it, what was their range of motion, how far did they reach, how often did they do it. So these are the quantifiable metrics that the clinician needs. And of course it has to go with, how do you engage the child in all of this? How do you make it engaging and dealing not only with their physical impairments, but a lot of these children might have cognitive impairments as well. Maybe they don't understand the rules. So how do you identify that and modify the protocol as well? And so what we want to do is look at what is this aspect of play therapy. And so we call it play therapy. So we talk about therapy, we're talking about children, and we talk about robotics. The terminology is play therapy, i.e. how do you do therapy in a play environment? So play is the natural function of a child. It's something, we go to work as adults, children go to play. It's how they learn, and that is their function. Their function is to learn until they get to a point where learning is minimized. And so the aspects we have to do in robotics of getting to this next stage is, what does play actually mean? Is it just random? Is it looking at everything around you? Or can you have it structured? Can you have a structured play environment where you have some very specific objectives? What does that look like? So we have to understand this whole concept of play therapy, because the robot has to understand and figure out what does it need to do in order to effect this play therapy. The other thing is, how do you monitor what the child is doing? Do you use perception? Do you use wearables? Do you use overhead cameras? What does that look like? And so this goes with giving the metrics is, what is the child doing? Are they doing it correctly? Are they doing incorrectly? How do I quantify that difference? What does that look like? If I need to grab something, am I just concerned about the object being grabbed, or do I also need to look at the entire arm kinematics? What does that look like? And how do I correlate that with what the clinician wants? So I have to understand the child's movement in that regard. And I have to understand two differences. So a child's natural inclination is to play, and they want to wander and they want to do exploration about their environment. But there's a very specific protocol that the therapist wants the child to do. Maybe the child needs to do a reaching operation. Maybe it's a transport operation. Maybe they have to change the range of motion of their shoulder. And so the clinician wants the robot to interact with the child in a very specific way. And so how do you go from having the child play to playing with some very specific objectives? And the robot has to not only figure out what the child is doing, but also take the child where they are and start changing them in terms of what it is that they want them to do. And so if we want to do range of motion and the child is not moving their shoulders, maybe the robot says, oh, I really like how you're picking up that car. Maybe lift it up a little higher. So what happens now is you're changing your range of motion of your arm. How do you have the child and direct the child to what the clinician wants them to do, but still what feels natural to the child? And so all of those challenges is really focused on this aspect of, how do you learn the environment? How do you learn what the child is doing? And how does a robot also learn their behaviors? All of this, so you can say, okay, that's easy. We've got that. We understand that. We understand manipulation of the environment. We understand path planning. We understand kinematic analysis. But the way we understand it is through our math and our kinematics and our equations. So how do you now take this information and provide it to the clinician? Because the clinician does not understand or is not trained to look at, okay, range of motion. So a range of motion might be 90 degrees, and it's not XYZ, theta to XYZ, theta 2. That is the language of the robot, not the clinician. And so in the clinical world, they have these metrics of evaluation. And they're sort of subjective, but they're based on tests. And so you might say, what I want to do is measure how well a child might grasp something. And so what I would do is I'd actually have a bunch of different objects and have the child grasp different ones, and I would note how many times they actually grabbed it, if they dropped any, and I count and come up with a metric of how well they did. Now, as a robot, we have to try to figure out, how do I quantify something like X, Y, Z, and theta into those metrics of, yes, they did it, they didn't do it, and how many times. And so the way that we do that is we actually look at all of these metrics of reaching kinematics, movement time, path length, jerkiness, and we normalize it, and we convert it into a language that the clinician understands. And all of this is mapped together so that we can then have robots that interact. And so some of these are the robots that we use for our therapy. The one at the top is Darwin, which is a commercial platform. And what we want to use Darwin for is two aspects. One is we want to use it for playing and interacting in terms of upper arm movements, but also on gait movements. So as an example, if I'm a child and I have an impairment such that my gait is not quite ideal, i.e. maybe I have a limp, maybe I have one side that's affected, and so what happens, like with anyone, if you're hurt and you have some type of limitation in your leg, you're going to favor the other leg. And so you're not going to put as much pressure. But we want that. We want you to put the pressure because we want to start training you so that you feel comfortable. A lot of these children have limitations in how far they can walk because they haven't strengthened up their weakened leg because they rely so much on their strong leg. And so we want to basically get them to move, 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 move. And so with a robot, what we can do is we can start playing a little game of soccer. We have soccer tournaments. We know how to play soccer. And so let's play a little bit of soccer game. It's play, it's fun, and it's a robot. And so you can naturally, you don't even have to try to get the robot and child to interact. So they're playing back and forth, back and forth. And then every so often, what happens is when your playmate actually makes a mistake, i.e. shoots the ball, kicks the ball to a different location, if you're already engaged, what you're going to do is you're going to go and you're going to get the ball for your friend and kick it back. So what we've done then is we've just instituted a gait protocol. The child is now walking in a direction that was very intentional, although they're playing. The child does not actually realize that they're actually doing a protocol. And then we're interacting back and forth, back and forth. We're playing a game, it's soccer. The robot is interactive, and all of a sudden, the robot makes another mistake and kicks it in another direction. Man, this robot is really stupid. But I'm going to go help my friend, and I'm going to go walk over and kick the ball back. And so we've shown that we can do a protocol like this for many, many, many times. And the child, even if the child gets tired of the walking, because they're engaged and they're playing with their robot playmate, they will continue. And this is the protocol. And the things we record how long, we can record where the placement was, we can record where they started and where they ended. And you can think of it as we're just creating a map of information that we can then decode to the clinician. Another application we can do is, we call this the Simon Says robot. And Simon Says is a robot that we want to do imitation for. And so our Simon Says robot is, it's the Monoi. So the Monoi is a kit that you can purchase and you have to put it together. And so what we did with Monoi is we wanted to do a Simon Says imitation game. And so the way that this works is that Simon, in fact we call it Monoi Simon, does something and says, okay, I want you to follow me, mirror me, lift up my arm. And the child does it or does not. But because we're actually looking at what the child is doing, if the child does not, we'll say interactive, you can do better. Let's try again. If the child does it, then that's good. If not, oh, come on, don't you want to play with me? And so we have this interaction. And so what we're doing is we're actually trying to map very specific kinematics in terms of range of motion. And so we can, again, play this over and over and over again, and it's a Simon Says games. And then we've done some aspects of music. And so all of these allow us to interact. Some other aspects of interaction also deal with, going to the next slide, how do you have this interaction? And so I just say, there's this interaction, there's both verbal interaction as well as nonverbal. And so when you do something well, typically the response from a parent or a clinician or a teacher is, good job, or you can do better, or let's try better next time. And so you understand through verbal as well as nonverbal communication the different things to do. And so we put those same types of behaviors on the robotic system in order to evoke that same reaction. If I do well, it's one thing to say nothing. It's you did really well. Raising your hands, you did really well. Or if you didn't do so well, man, I hope you can do better next time. Let's try. And so just by changing your verbal as well as your nonverbal behavior, you can evoke that interaction so that the robot is a playmate. The robot is interacting. And again, at the end of the day, there's still a therapy protocol. The child thinks it's play, but at the end of the day, they're actually doing therapy. And so some of the interactions we have a conversation, we have head shakes, we have interaction in terms of surprise and happiness. We have things like good job and all of these aspects. And so we've pretty much, and this is just a sampling of some of the interactions that we have, and we pretty much have the gamut of any type of interactive behavior that either shows excitement, good job, or maybe we should do it next time. And so we've done studies about how do people evoke certain responses. Typically, there's wide stances that says, I'm very happy. There's very shallow stances, i.e., I'm sad. And so we've looked at how humans interact with their body languages and their voice in order to evoke those same kinds of reactions. And I've done studies to figure out what does that look like. One of the things is eye contact, as an example. Eye contact is very important between a robot and child because that says, I see you, I know what you're doing, now follow me. And so you can do things like imitation just by doing eye contact. Or if I'm playing my back and forth soccer game and I shoot the ball and I look at it, all of a sudden the child looks as well. It's like, oh, it's the ball, the little silly robot, let me go get it for you. So eye contact also becomes very important in tri-gaze. I look at you, I look at the object in question. You obviously know. Oh, obviously you want me to go get that object. And so all of this body language we also put on the robot system itself. And so some other things that we've done in terms of this therapy aspect is if we have a child and we have this interaction, what happens if you have a child that has no gait, i.e. is in a wheelchair, still needs some therapy in terms of upper arm movements? How do you interact with the robot as well? And so we've looked at combining robots and tablets. So tablets are another form of games. They're another form of play. And in fact, there's a lot of therapy apps that clinicians use that do things like cause and effect. If I see something, I need to press. Or if I wanted to go from one point to another, I can use my stylus, I put it in, and even though I might have a closed fist, I can touch this and drag it. And so what I'm doing is aspects of therapy, but in this 2D world. And so what we want to do is look at combining all of this together. And so the way that we can do this is, here's our robot, and we have a child. This actually has a child with a disability, very good upper arm movement. And the interaction involves some of these aspects of the behavior interaction in terms of expressiveness and disappointment. But what the child is doing is interacting with the game. And so here's our disappointment because child didn't do too well, maybe didn't follow, pay attention, didn't follow the rules. And then there's happiness as we won together. And so what we've shown is that when we have these therapy apps that the child will do, typically they're actually not as exciting as they could be, but all of a sudden this therapy becomes exciting because you have this robot that you can do it with. And so all of this together is really designed to have robots function as healthcare robotics in a therapy type of environment by using this concept of play. And so lastly, I just kind of gave an overview of therapy and healthcare robotics and focused on children because of this play therapy, but it also applies to adults. The play is a little bit different, and so you could do things like kitchen scenes and more occupational scenes, like how do you figure out where your keys are or grab your keys, but the whole concept of interaction and having this entity that is seeming almost human, is social, actually improves on the therapy. Now, one of the last things I want to mention, and this is primarily because in general there might be some fear in the community about robotics. In healthcare robotics, believe it or not, the fear is not based on, oh, my robot is going to do something bad. The fear is relying on this robot. And so what we've seen is that in the domain of healthcare robotics, because these robots function in a medical application, i.e. you always trust your doctor. I mean, even if the doctor is wrong, you don't know that. You trust your doctor. And so what we find is in healthcare robotics, people have this natural inclination of trusting their robots because they're medical, they're doctors, they're with the clinician, the therapist is monitoring them, so they must always be right. And so one of the things that we're very conscious of in healthcare robotics is ensuring that what we do in this domain makes sense, is ethically reasonable, is legally reasonable, because there are a lot of individuals who would be willing to do anything just for a chance for quality of life. And that doesn't necessarily mean as roboticists we should do it. And so it's one of the things that we as roboticists and healthcare have to consciously be thinking about, because you have volunteers that say, I don't care what you do, if I even have one chance of improving my quality of life, I'm okay. And if the robot breaks my arm, I'm okay because I might actually now can move and grab things that I couldn't before. And so we as roboticists really have to be conscious about that reliance and that obvious trust from the very beginning, because we are in a domain that people naturally trust, which is this medical region. And so that's just one of those things that we as roboticists always need to be conscious of in the domain of healthcare robotics. And so with that, I conclude my lecture, and I thank you.